Swayam Prabha. Digital India. Educated India.
Welcome friends to this fifth lecture of week 5 of this NPTEL online certification course of environmental soil chemistry, and in this week we are talking about ion exchange processes in the soil. In the previous 4 lectures we have discussed different aspects of ion exchanges. We have broadly defined what is ion exchange, and then we have also discussed what is cation exchange capacity, what is anion exchange capacity, and why cation exchange capacity is important from the soil fertility point of view, and also we have discussed why anion exchange capacity is also important from the soil fertility point of view. Apart from that, we have discussed how we can measure the cation exchange capacity in the soil, and I have showed you different processes, different protocols which we basically use in the laboratory for measurement of cation exchange capacity. Remember, we have talked about the ammonia distillation method, which we generally use for measuring the measuring the cation exchange capacity. Remember, cation exchange capacity is generally expressed in terms of centimole of charge per kg of soil, and both cation exchange capacity and anion exchange capacity depends on soil pH. If soil pH increases due to the variable charge, the cation exchange capacity also increases, and cation exchange capacity is also related to percent base saturation. Remember, percent base saturation is the fraction of the cation exchange capacity which is basically accounted for the calcium, magnesium, sodium and potassium, and the two acidic anions such as acidic cations such as aluminum and H plus are not included in the calculation of cation exchange capacity. Now, or percent base saturation. In the last class, in the last lecture, we have talked about, we have started the CEC numerical problems, and we have discussed couple of very short CEC cation exchange capacity numerical problems. Remember that I just want to give it a very quick review of whatever we have discussed regarding the numerical problems. So, remember that 1 mole of any substance, that it could be either element, molecular, compound, is the atomic mass of the element, molecules and compound, and the mass of 1 mole of hydrogen is 1 gram, and the mass of 1 mole of calcium ion is 40 grams, whereas 1 mole of nitrate is always 62 grams. Now, in many chemical application, a mole is basically a too large, too big unit to easily manipulated. So, that is why we generally use centimoles, which is basically 1/100th of a mole, and millimole, which is 1/1000th of a mole instead of a mole. So, we use either centimole or millimole instead of a mole, and the mass of centimole of hydrogen in for 0.01 gram, and for millimole is obviously 1/1000 of 1 gram, that is 0.001 gram or 1 milligram. So, moles of charge are the same as moles of anything else. So, 1 mole of charge is the charge, either it is positive or negative, of 1 mole of ion, which is either either a plus 1 or plus negative charge. An ion such as calcium 2 plus has 2 moles of charge for each mole of calcium atoms, because it has a 2 valency, and a trivalent atom such as trivalent atom such as aluminum has 3 moles of charge per moles of aluminum. And another major rule we have discussed, that is 1 mole of charge of any ion will always be equivalent to 1 mole of charge of any other ion. So, this makes the 1 mole of charge, that is molar charge, a handy unit when discussing cationation capacity in soils. And remember that in the soil, just like a mole, the molar charge is also too big number to easily manipulated. So, that is why we generally use centimole of charge, which is actually 1/100th of molar charge. But and we express the catenation capacity as centimole charge per kg of soil. So, we started with this problem, that is what is the mass of 1 mole, 1 centimole and 1 millimole of following cations and anions, and I showed you, we have seen these cations like H plus, Ca2 plus, Na plus, K plus, SO4 2 minus, NO3 minus and HCO3 minus, and we know that mass of 1 mole of these atoms are basically these ions are 1 gram, 40 grams, 23 grams, 39 gram, 96 grams, 62 grams and 61 gram. From that we calculated 1 centimole, which is actually 1/100th of this mass of 1 mole, and then we calculated mass of 1 millimole, which is 1/1000th of this mass in 1 mole. So, in the second problem we talked, our question was what is the weight of 1 mole of charge, that is molar charge, and 1 centimole charge of same cation and anion. So, in that problem we just basically divided the molar charge, molar mass with the number of valencies. So, in case of H plus obviously it will be 1, in case of C2 plus the valency is 2. So, we are getting a mass of molar charge of 20, similarly 23 for sodium, 39 for potassium, 48 for sulphate, and then 62 for nitrate and 61 for bicarbonate, and from there we calculated the centimolar charge, which is 1/100th of the molar charge. In the third example we talked about what is the weight of the calcium chloride you would require to replace 4 molar charge of calcium in the soil. So, you need to replace 4 molar charge of calcium. So, you need at 4 molar charge of you need to remove you need to remove 4 molar charge of potassium. So, you need to apply 4 molar charge of calcium. So, for from the equation, from the formula of CaCl2 we know that 1 mole of calcium ion produce 2 molar charge. So, basically to supply 4 molar charge we require 2 moles of calcium chloride, which basically weights 2 into multiplied by 111, that is molar weight. So, basically 2 grams of calcium chloride to supply 4 moles of charge of calcium, which will further replace 4 moles of charge of potassium from the soil. And fourth question was how many moles of molar charge of potassium does it take to replace 12 molar charge of calcium. So, for 12 molar charge of calcium we require 12 molar charge of potassium. We remember that 1 molar charge of any element or any atom, any ion can be replaced by the 1 molar charge of any other atom irrespective of their valency. The fifth question we have talked about, that what weight of potassium is required, potassium ion is required to replace 12 molar charge of calcium ion. So, we have calculated 12 molar charge of potassium will be required to replace 12 molar charge of calcium. So, we basically have to just calculate what is the weight of 12 molar charge of potassium, and from the table which we have shown already we know that it is 468 grams. In the sixth problem which we solved last, what weight of calcium 2 plus is required to replace 12 mole of K plus. So, we know that to replace 12 mole of K plus we require 12 mole of Ca2 plus, and 12 mole of Ca2 plus basically coming from 6 moles of 6 moles of calcium chloride. So, basically or 6 moles of calcium chloride or 6 moles of calcium. So, 6 multiplied by 20, 6 multiplied by 40 is basically the 240 grams, because we know that 1 moles of calcium ion equals to 40 grams. So, 6 moles of calcium ion will be 240 grams. So, this 240 grams of calcium 2 plus ion will be required to replace 12 moles of potassium. So, The next problem says the what weight of calcium carbonate is required to replace to 12 molecular charge of potassium ion. So, in the previous problem we have already determined that to replace 12 molecular charge of potassium, we require 12 molecular charge of calcium ion. So, 12 molecular charge of calcium ions is equal to 6 molecular 6 molecules of 6 moles of calcium 2 plus ion. So, each if we consider that each mole each mole of calcium is coming from the calcium carbonate. So, each mole of calcium carbonate is basically equals to 100 grams, we know that the molar mass of calcium carbonate is 100 grams. So, 6 moles will be equal to 6 into multiplied by 100, that is 600 grams. So, that is why we need a total of 600 grams of calcium carbonate to replace 12 molar charge of potassium. Now, the 8th question was what is the cationation capacity of a soil that has 6 molar charge of H plus, 6 molar charge per kg of calcium 2 plus ion, then 2 molar charge of per kg of magnesium ion and 1 molar centimolar charge of K plus ion and sodium ion each. So, basically we have to calculate the cationation capacity, it is very simple. So, if you assume that you have removed 100% of these ions then from the exchange complex of the soil, then you need to sum all the centimole charge which we are seeing here. So, basically if we sum up all this 6 centimole charge plus 6 centimole charge plus 2 centimole charge when 1 plus 1 centimole charge, we will get the answer is 60 centimole charge of per kg of cationation capacity. So, these are relatively very short and simple question. Now, the 9th numerical problem is what is the weight of H plus Ca2 plus and Mg2 plus, K plus and sodium plus on the exchange complex in question 8. Now, we know that to determine the mass we need to multiply the number of centimole of charge by the mass per centimole of charge. So, we need the units are the centimoles are not in the moles. So, from the answer in problem 2 which I have already shown you, we know that what is the mass per centimole of charge. So, basically we have to multiply it. So, we know that centimole charge of per kg on exchange complex is 6 centimole charge per kg for hydrogen. In case of Ca2 plus it is 6 centimolar charge per kg and in case of Mg2 plus it is 2 centimolar charge per kg, in case of K plus it is 1 centimolar charge per kg, in case of sodium it is 1 centimolar charge. Now, we already know from table 2 or from problem 2 that the mass per centimolar charge is 0.01 gram for hydrogen, 0.20 gram for calcium, for magnesium it is 0.24 gram, for potassium it is 0.39 gram and for sodium it is 0.23 gram. So, basically we have to multiply it for each cations to get ultimately their mass in gram per kg of soil. So, this is the basically answer for this question 8. So, if we move question 9. So, if we go to question 10, question 10 says that if the cationation capacity of a soil is 30 centimolar mole charge per kg, how many centimole charge of H plus, Ca2 plus, Mg2 plus, K plus and Na plus are on the exchange complex if the exchange complex has 5% H plus, 50% Ca2 plus, 20% magnesium 2 plus, 23% K plus and 2% sodium plus. So, basically what is the weight of each of these cations on the exchange complex? So, we know that percentage of each ion on exchange complex is 5 in case of H plus, 50 in case of Ca2 plus, 20 in case of Mg2 plus, 23 in case of K plus and 2% in case of sodium plus. Now, we already know that the catenation capacity of the soil is 30 centimolar charge per kg of soil. So, basically if we multiply the CEC with the percentage of iron in the exchange complex, we will get the centimole charge per kg of soil for each of the ion. That means, in the 30 centimolar charge of per kg of soil, that is in the total CEC, what is the contribution of individual ion we can get by multiplying the total CEC with the fraction of individual ion. So, in this fashion we are getting this value. For H plus we are getting 1.5 centimole charge per kg. In case of calcium we are getting 15 centimolar charge per kg. In case of magnesium we are getting 6 centimolar charge per kg. In case of potassium we are getting 6.9 centimolar charge per kg, and in case of sodium we are getting 0.6 centimolar charge per kg of soil. Now, what is the weight of these ions on the exchange complex? Now, we know that the mass of centimole charge, so basically if we multiply the mass of centimole charge with this centimole charge per kg, so basically we will get the weight of these cations. So, in case of H plus we are getting 0.015, in case of calcium we are getting 3 gram per kg, in case of magnesium ion we are getting 0.72 gram per kg, in case of potassium ion we are getting 2.69 gram per kg, in case of sodium we are getting 0.138 gram per kg. So, this is how we solve question 10. So, let us move to our last question. So, last question says that if a soil has a CEC of 25 centimole, so if a soil has a CEC of 25 centimolar charge per kg and 12% of the exchange capacity is saturated with sodium, what weight of calcium sulphate must be added to 1 kg of soil to remove 1/2 of the sodium from the exchange complex when we are assuming 100% efficiency? Now, here one thing is important, we need to first calculate that what is the CEC which is basically contributed by sodium, and then half of the CEC is basically replaced by calcium in the form of calcium sulphate. So, if we remember this thing, if we can sort out this thing, the answer will be very easy. So, first we have to find out how much sodium is in the exchange complex. Now, we know that the if 12% of the CEC is occupied by sodium, then 0.12 multiplied by 25 centimole charge per kg, because this is the total CEC. So, basically the sodium is accounting for 3 centimolar charge per kg. So, this is the basically the centimolar charge per kg contributed by the sodium. Now, the problem is to replace, that is 1/2 of the sodium with calcium from gypsum. So, we need to replace half of 3 centimolar charge per kg, that is 1.5 centimolar charge per kg of sodium with the same number of centimolar charge of calcium, because we know that according to the thumb rule that 1 centimolar charge of any cation can replace 1 centimolar charge of any other cation. So, similarly 1.5 centimolar charge per kg of sodium will be replaced by 1.5 centimolar charge per kg of calcium. So, basically we need to add 1.5 centimolar charge of calcium in the form of gypsum. Now, we know that each centimole of gypsum basically carries 1 centimole of calcium and 2 centimole of 2 centimole charge of calcium. So, basically we have to supply 1.5 centimole of charge of calcium. So, if we simplify it, we will basically get that we need to apply 1.02 grams of calcium sulphate in this fashion to basically supply the required amount of calcium to replace half of the sodium in the exchange complex. So, this is how you can solve it. Now, you know that how we get this 1.02 grams. So, we know that the mass of 1 centimole of gypsum is basically 1.36 gram. So, 1.36 gram basically contains 0.40 gram of calcium and 0.960 gram of sulphate. So, the weight of 1 centimole charge of calcium from the gypsum is 1.36 grams calcium sulphate per centimole of gypsum divided by 2 centimole charge, because here the calcium has 2 valency. So, we need to add basically 0.68 gram of gypsum per centimole charge replaced. So, right now when we want to replace 1.5 centimole charge, basically we have to multiply 0.68 into 1.5. So, basically that will give 1.02 grams. So, that amount of calcium sulphate need to be applied to the soil to replace that half of the sodium in from the exchange complex. So, this is how we solve these different types of catenation capacity related numerical problems. Now, let us go to a new topic, that is catenation equilibrium constant and selectivity coefficients. Now, many attempts to define the equilibrium exchange constant have been made, since such a parameter would be useful for determining the state of ionic equilibrium at different ionic concentration. Now, some of the better known equations which we are going to discuss today are Kerr's equation, Van's law equation and Gapon's equation. So, these three are major equations which basically use for calculating the catenation equilibrium constants. So, in many studies it has been shown that the equilibrium exchange constants derived from this equation are not constant, as the composition of the exchanger phase or solid phase or solid surface changes. So, if we remove, if we basically consider that soil is a solid and which is basically in equilibrium with the surrounding soil solution, then based on the composition change of the solid surface, the equilibrium exchange constants also varies. So, this has been reported by several studies. Thus, it is often better to refer to them as the selectivity constants. Instead of equilibrium exchange constants, we generally prefer to use these selectivity coefficients rather than exchange constants. So, let us first discuss the Kerr's equation. Okay. Now, according to Kerr in 1928, he proposed a equilibrium constant in soil. Now, the soil was a solid solution, as I have told you, because it is basically a macroscopically homogeneous mixture with a variable composition. The soil is very heterogeneous mixture. So, it has a variable composition. So, for a binary reaction, so what is a binary reaction? Binary reaction means a reaction involving two ions. So, here you can see this is a binary reaction where these A is basically A and these B are basically exchanging cations and X represent the exchanger. In case of this reaction, it is basically soil solid. Okay. Now, this AQ represent basically the aqueous phase and H represents the solid phase. So, basically what happens in the aqueous phase, these A ion, and in the solid phase this B ion is basically adsorbed. So, during the ion exchange process, this B will from the exchanger solid exchanger will be replaced by this A. So, ultimately this B will be coming to the aqueous phase and A will get adsorbed into the solid phase. So, this is basically a binary reaction. So, based on this binary reaction, Kerr has proposed a constant. So, Kerr expressed the equilibrium constant, or more correctly a selectivity coefficient for that equation, and he denoted that equilibrium constant or selectivity coefficient as Kk, where basically it is taking this formula. Now, in this formula, these brackets basically indicates the concentration of the aqueous phase, and these braces basically represents the concentration in the solid or exchanger phase. So, one thing is clear, basically this is a ratio between the the concentration of the ion in the aqueous phase as well as the concentration of the ion in the multiplied by this concentration of the ions in the solid phase. So, this is called equilibrium constant by Kerr. Now, Kerr studied a typical exchange system, that is calcium and magnesium exchange system, and found that this Kk or this constant value remained relatively constant as exchanger composition changed. So, although the exchanger complex changes or composition changes, that means although the soil composition changes, this constant Kk remains same. Now, this indicated that system behaves ideally, that is the exchanger phase activity coefficient for two cations were each equal to 1. Now, he was kind of he was fortunate, because calcium magnesium exchange is one of the few binary exchange system where ideality is observed. In most of the cases, this ideality is not present. So, what will be the catenation constant in those situation or non-ideal situation? To solve that problem, Albert Vanslo, another scientist, was he first introduced the ion exchange in thermodynamical context. So, considering the binary cation exchange reaction in equation 1, we have already seen this equation. So, he described the thermodynamic equilibrium constant as Keq, okay, thermodynamic equilibrium constant Keq. So, basically this parenthesis basically indicates the thermodynamic activities. So, instead of concentration, it is basically thermodynamic activities. Now, we know that it is not difficult to determine the activity of a solution component, since the activity we already know from our previous chapter or previous week discussion that activity of solution component, since the activity would equal to the product of equilibrium molar concentration of the cation multiplied by its solution activity coefficient. So, basically if we basically multiply, for example, in case of this cation A, if we multiply the the equilibrium molar concentration with their solution activity coefficient for both the cations for A and B, we will get there basically the activity of the solution component. So, Ca and Cb here are the equilibrium concentration. So, C and Cb are the equilibrium concentration of A and B respectively, and these two terms are basically solution activity coefficients of these two cations. So, solution phase activity coefficient calculation is not problematic. The problem comes when calculating the activity of the exchanger phase. It is not that simple. Now, Van's law defined that the exchanger phase activity in terms of mole fraction. He basically expressed this exchanger phase activity in terms of mole fraction, that is NF and NB for ions A and B. So, thus according to Van's law, equation 3 could be rewritten as, you can see this is the equation 3 we know, and basically this is, so this exchanger phase is basically represented by this mole fraction, okay, where this mole fraction can be represented by these two equations. So, we can basically simplify these as this Van's law coefficient, and you can see this term is basically multiplication of this solution activity coefficient of that particular ion with the equilibrium molar concentration and multiplied by molar fraction of that particular ion. Okay. So, this is how this ratio will calculate this Van's law coefficient. Now, he assumed that this Kv was equal to Keq. However, he failed to realize one very important point. The activity of a component of a homogeneous mixture is equal to its mole fraction only if the mixture is ideal. So, if the mixture is ideal, then Fa equal to Fb equal to 1, where Fa and Fb are the exchanger phase activity coefficients for cations A and B respectively. Now, if the mixture is not ideal, then the activity basically will be a product of molar fraction and this F, which is where F is the exchange phase activity coefficients. So, for this Keq will now tend this form. So, this was previously there, it is basically now we are basically multiplying this Fa and Fb with this molar fraction to express this Keq in terms of Kv and the ratio of the exchanger phase activity coefficients. So, this is how you can simplify K equal to Kv multiplied by the ratio of exchanger phase activity coefficients. So, where these basically Fa and Fb, we know that this will take these two forms. So, basically if we ultimately see, the Vance law coefficient will be equal to Keq multiplied by Fb by Fa. Okay. So, Kv is an apparent, Kv now it is called an apparent equilibrium exchange constant or cation exchange selectivity constant. So, basically by rearranging that we get this final form in the form of equation 8. So, this is called an apparent equilibrium exchange complex. So, basically Kv equals to Keq or equilibrium constant when it is multiplied by the ratio of these Fb and Fa or exchange phase activity coefficients. Now, other empirical exchange equations are Krishnamurti, Overstreet. They basically used a statistical mechanical approach and include a factor of valence of the ions to obtain a selectivity coefficient, that is Kk0. For monovalent ion, they got this got this value of 1. For divalent ion, they got this value of 1.5. For trivalent ion, they got this value of 2. Now, another equation was given by Gaines and Thomas, and also Gapon, another scientist, also gave a exchange equations, other empirical equations. Also, they introduced exchange equations that yielded selectivity coefficient. In case of Gaines and Thomas, we know it is Kgt, and in case of Gapon, it is Kg respectively. So, for Ka-Ca exchange on a soil, the Gapon convention would be written as Ca half soil plus K plus, then K plus half of Ca2 plus. So, here you can see that here the exchange is going on with chemically equivalent quantities. It is very important. It is chemically equivalent quantities of the exchanger phase and the exchangeable cation. So, this is the special characteristics of Gapon's equation. So, the Gapon selectivity constant for Kca exchange will be equal to this. It is very simple. This is where brackets express the concentration in the aqueous phase and this braces represents the concentration in the exchange complex or in case of soil. Now, the selectivity coefficient obtained from this Gapon equation has been most widely used in soil chemistry and appears to vary the least with the exchange phase composition changes. So, you can see here different scientists have given different selectivity coefficients like Kerr, Vance law, Krishnamurti, Overstreet, Gaines, Thomas and Gapon. So, this is basically a combination of different selectivity coefficients for homovalent exchange, where in case of homovalent exchange, the example is when the potassium sodium type of exchange, that is called homovalent exchange, and when there is a potassium calcium type of exchange, then it is called heterovalent exchange. So, for both type of exchange, these selectivity coefficients are already given. Thermodynamics of ion exchange, also thermodynamic equation provides relationship between the exchanger phase activity coefficient and exchanger phase composition, and these equation basically demonstrated that calculation of an exchanger phase activity coefficient, we already know that exchanger phase activity coefficient is basically a ratio where A is the activity in the exchanger phase and N is the molar fraction, we know that. Now, the standard state for the absorbed phase is the homoionic exchanger in equilibrium with a solution saturating cation at a constant ion exchange. So, we already know this formula which we saw in case of Vance law equation. So, assume that any change in this Kv, with regard to exchanger phase composition occurred because of a variation of a exchanger phase activity coefficient. So, if we simplify this equation by taking log, so we will basically take it will basically take this form of 11. Now, after taking this log, if we take differential, this will again take this form of equation 12. So, basically by taking this Vance law coefficient, we are taking the log, and by simplifying the log we are getting these two different equations. So, once we get this differential equation, remember that any change in the activity if Bx that is in the reactant phase, in the reactants, when there is an activity change in the solid exchanger phase, that will be accompanied by a change in the activity of the product, in the product also, in the solid phase of activity of the product also, such that the mass of the exchanger is conserved. So, this necessity as an application of Gibbs then Duhem equation can be expressed in terms of this. So, this is basically equation 13. So, equation 12 and equation 13 we can solve, and basically we can get this equation 14 and equation 15. Now, from this equation 14 and 15, another important thing is that this, if you see this equation 14, one thing is clear, NB by NA plus NB and NA by NA plus NB, these two are basically, this NA by NA plus NB is basically EA, which is an equivalent fraction of AX, and EB is basically equivalent fraction of BX. So, basically if we put these values, we will finally get, in terms of EA, if we basically, if we put the values of EA in equation 14 and 15, that will become basically this. So, equation 14 will become equation 16 and equation 15 will become equation 17. So, basically we are basically inputting the value of EA into equation 14 and 15 to get equation 15 and 16. So, integrating equation 16 and 17 by parts, finally we will get this equation 18 and 19. So, what is the need of saying all these things? We can see that these are the final two equation 18 and equation 19. So, substituting these equations of equation 18 and 19 to equation 11, basically equation 11, you know that this is equation 11, which we started by taking the logarithm of Van's law equation. So, by inputting all this value into this equation 11, we will basically get this final value, which provides for the calculation of thermodynamic equilibrium exchange constant. So, thermodynamic equilibrium exchange constant. So, if we basically plot from this equation, from this integral equation, it is clear that by plotting this kV and EA and integrating under the curve from EA 0 to EA 1, one can calculate this KEQ. So, basically if we plot this kV versus EA and integrate from EA values of 0 to 1, we will basically can calculate KEQ. So, one can calculate KEQ or ion exchange studies KEX, the equilibrium exchange constant. So, this is how the thermodynamic concept is highly integrated with the ion exchange process, and using this thermodynamic principle we can calculate different types of equilibrium or exchange constants. So, equilibrium exchange constants. So, I hope that guys you have learned something new in this ion exchange processes lectures, and these are three references: environmental soil chemistry by D. L. Sparks, the nature and properties of soil by Niles C. Brady and Will, and principle of soil chemistry by Kim H. Tang. I know that I cannot cover all these things due to time constraint. However, if you are interested, these books will be very much helpful to understand this process in more details. So, I hope that you have learned something new in the cation exchange process, and cation exchange capacity and anion exchange capacity is now more clear to you. So, let us wrap up this week 5 of lectures, and let us meet in week 6 of lectures to discuss other aspects of environmental soil chemistry. Thank you very much.